the topic today, implicit differentiation. It corresponds to section 3.5 in the textbook. So what we're looking at today is, so far, we have only dealt with explicitly written functions. So y equals, or f of x equals, and then x is all on the other side. So the equations are solved for y. Implicitly written functions, or equations, implicitly written equations are all kind of mixed up. X's and y's together, usually on the same position side of the equation, interacting with each other. The equations aren't solved for y. So we want to have a way to take the derivative of those also. So let's look how this plays out with something we are used to, the derivative with respect to x of x cubed. So you know power rule, 3 comes down, x decrease exponent by 1. Sorry, whatever, -2, going crazy. Okay, now you're taking the derivative of x, so the derivative of x with respect to x. So this numerator here is the rate of change of x. This denominator represents you doing this with respect to x. Now here's the thing, we've been doing this all along, dx over dx, but we don't really write it because dx over dx, rate of change of x with respect to x, they usually just cancel out something over self. So you would just have 3x squared, which you know with the power rule. Now let's go here, ddx of y cubed. Now power rule, bring the 3 down, decrease exponent by 1. I did it again. I think it's because I'm saying decrease, I'm writing minus. Got to stop doing that. So decrease by 1, so 3y squared. Now, you took the derivative of a y variable. So you're finding rate of change of y with respect to x. And you have your answer. Those don't cancel out. So, fundamentally, we're finding rates of change with respect to a variable. When those differ, you have to write that fraction, the rate of change of this variable with respect to that variable. And if this and that are the same, cancel out. If this and that are different, then you leave them. So, dy dx, dz dx, db dx, dr dx. What we're looking at is taking the derivative with multiple variables involved. This leads to a topic known as related rates, where in the real world, there's a lot of things happening once. There's a lot of variables to account for. When you take the derivative of a certain situation, you're taking the derivative of multiple variables at one instant, and then you get to relate them all together. So usually, as systems change, as situations occur, there's a single constant that bounds all of them together. That constant is time. So what we'll see pretty soon is you're taking the derivative of whatever variable, but you're always taking it with respect to time. So dr dt, the rate of change of a radius with respect to t, time. dh dt, the rate of change of the height of an object with respect to time. Here we have a sum of difference. Derivative of x, just 1. Derivative of y, just 1. But because y is not x, you need the dy dx. Example D, d dx of x y squared, and this is the product rule, x times y squared. So if you need to, kind of set it up over to the right real quick. Oh, this is not far enough to the right. Go further, okay. V is y squared, so u prime is 1. V prime would be 2y dy dx. Now you have your puzzle pieces. Go ahead, put your puzzle pieces together. So the two cross diagonals. So x, well, we'll do y squared times 1, y squared, plus x times 2y dy dx. So really, implicit differentiation at its core, just take the derivative like you know and love how to do already. But if you're taking the derivative of a variable other than the one you're doing with respect to, you need that marker, d whatever, dx. Now let's say we want to find dy dx, so then you need to solve for dy dx, so really solve for y prime, okay? We'll start out like we did above, take the derivative of what you have, so 3y squared dy dx plus 2y dy dx minus 5 dy dx minus 2x equals, now here's the tricky part, don't forget this, take the derivative of the other side also. Derivative of -4. Derivative of any number is 0. Now we want to solve for dy dx. So get all the dy dx's on one side. Get everything else on the other. So let's start with the 2x. So let's add that 2x over. So plus 2y dy dx minus 5 dy dx equals, adding 2x over, 2x. Now look on the left side of the equation. Every single term has dy dx. Alright? Now think, when you distribute like x times y plus z, that quantity, distribute the x in, you get xy plus xz. You take your single x, distribute, and you get multiple x's. Now we want to reverse that. We have multiple dy dx's. We only want one. So let's factor out. So every term factor out dy dx. So factor that out. The leftovers go in parentheses. So remember, you have to leave that trail of breadcrumbs in case you want to go backwards. So leave your leftovers. So if you want to distribute the dy dx back in, I don't know why you'd want to, but you can. So from here to here, you are factoring. So now you have dy dx by itself factored out. Now let's get it truly, completely by itself. So you get leftovers in parentheses, divide those over. 5 minutes, get to class. So 2x over the quantity 3y squared plus 2y minus 5. And you have solved for dy dx. So, I mean, every problem could look different, but there's your general steps. Implicit differentiation. Kind of get this out so I can show you. Implicit differentiation. Get all the dy dx's on one side. Factor dy dx out. Divide your left rows over. Now here, consider this equation, x squared plus 4y squared equals 4. Now you've seen this before, okay? Last year, when we looked at conic sections, okay? Take everything, divide everything by 4. So y squared over 4, or sorry, x squared over 4 plus y squared equals 1. You have the equation of an ellipse, okay? That ellipse centered at the origin, a major axis length of 4, so 2 to the right, 2 to the left, a minor axis length of 1, so 1 up, 1 down, and then I'll do my best to kind of make the oval, and that is okay. You know what I'll try? Let's try the shapes. Okay, so try this and see what happens. Okay, I'll leave it there. Good enough. So, graph that. Part B, find the y dx for the above equation. So I'll go back to the original equation. Right here, x squared plus 4y squared equals 4. Take the derivative of that. X squared gets you 2x. 4y squared gets you 8y. dy dx. And don't forget, derivative of the other side, 0, okay? So we want to get dy dx on one side, everything else on the other, so let's start that process. We're going to do, oh yeah, we'll start the process, so 8y dy dx equals negative 2x. Divide by 8y, dy dx equals negative 2 over 8, so negative 1 over 4. Alright, so negative x over 8y. Now, we got at this point to realize something. That negative x over 4y, that is dy dx. dy dx is y prime. That is still the derivative. So that means if it's your derivative, it's also slope. It is also rate of change. So you want to think about those terms. They're kind of synonymous with each other. Derivative can give you slope. Slope is rate of change. They're all kind of related, okay? dy dx, yeah, this is a different process. It's implicit differentiation, but it's still differentiation. You're finding a derivative. So hey, we just saw this the other day. Find the slope of the tangent line to the curve at the point. Root 2, negative 1 over root 2. So find the slope. Hey, dy dx is a derivative that is the slope. Make sure in class is now time. So dy dx, let's solve that. So negative x over 4y. So negative root 2 over 4 times negative 1 over root 2. Now let's simplify this down. Negative root 2 over negative 4 over root 2. And in math, we don't divide by fractions. We usually multiply by the reciprocal. So negative root 2 over 4. This gives us negative root 4 over 4. This is negative 2 over 4. Negative 2 over 4, more commonly known as negative 1/2. So our slope at that point is negative 1/2. Look back at the graph. Root 2, negative 1 over root 2. We're about here. So slope of, it's negative, it's root 2, negative 1 over root 2, yeah. Oh my gosh, I made a mistake. Like negative 1/2, that doesn't fit. What's going on? So, when I divided by negative 4 over root 2, multiplied by negative root 2 over 4, negative times a negative, come on, rookie mistake. That's a positive. You get so caught up in what's going on and all these big ideas. Don't forget the little ones. So, slope of positive 1/2. At this point, root 2, negative 1 over root 2 right here. Yeah, we have a positive slope, about 1/2, okay? Now part D. Write the equation of the tangent line. Now, equation of a tangent line. I don't want that highlighter right here. Remember, I told you, you're going to see this a lot. In a lot of different kind of situations, a lot of different contexts. Remember, point slope form. Y minus y1 equals m, quantity x minus x1. Hey, guess what? We found m. We found the slope. It's right there. Hey, guess what? We have a point. x1 and y1. So go ahead, make the equation. So y minus y1, y minus negative 1 over root 2 equals a slope 1/2 x minus x1 root 2. Alright, same kind of problem, same process, but a different context. Again, finding the equation of a tangent line. You're going to see that a lot this year, okay? Part D, don't worry about part D. If you want to, go for it, but you don't have to. Go ahead and look at example 4 and example 5. Check your work with my completed notes online.